All right, this is our Unit 2, Lesson 5 for our calculus class. The unit is called Derivatives, and the Lesson 5 is called Power Rule. So what we're going to learn in this lesson is distinguishing power functions from other functions, and then once we found those power functions, how to use the power rule to find the derivative. So a power function is a function in the form of, x to the power of some number n, and n is some real number. Okay, so if we look at these, we have some examples and some non-examples. X to the power of 5 is definitely a power function. Trig function, not a power function. This one's deceptive. 2 to the power of x is not a power function. Remember, the base has to be an exponent, and the exponent has to be, the base has to be a variable, the exponent has to be a number. So this one's reversed, so it's not a power function. It's exponential, actually. Because there's a plus sign in the denominator here, this is technically not a power function. This one is a power function, x to the power of e. E is a number, 2.718, so this would be a power function. Great question in class. What about x to the power of x? Well, it does have a base of a variable, but its exponent is not a number. So for that reason, not a power function. Okay, back to the second column at the top. 1 over x squared can be written as x to the power of -2, and so that would count as a power function. We just have to manipulate the writing of it a little bit. Absolute value of x, not a power function. A variable to the power of a fraction, well, the fraction is also a number, so that's a power function. Square root, remember, square root can be written as a rational exponent, so this could be written as a power function. E to the power of x is not a function, not a power function, for the same reason 2 to the power of x isn't. The base and the exponent variable number have to be reversed. And the last one, 1 over x is a power function. It can be written as x to the power of -1. All right, so here's how the power function, or the power rule, works. So if you have a power function where n is some real integer, then the derivative of y with respect to x would be n times x to the power of n minus 1. So in other words, you just bring the exponent in front of the x and multiply it by the coefficient, and then your new exponent is just 1 less than n, which, in comparison to writing, the limit as h approaches 0 of f of x plus h minus f of x over h, this is much simpler. How nice. Examples. So here are some power functions. If I use the power rule on these things, the derivative, or f prime of x, would be, we multiply the coefficient by the exponent, so multiply by 5, and then take x and take its exponent and subtract 1, so 5 minus 1 is 4. So f prime of x would be equal to 5x to the power of 4. G of x is 3x squared, so g prime of x would be the 2 times 3x, and then our exponent would be just 1, 2 minus 1. So if we simplify this, we get 6x as our derivative. Notice the h of x is just a number, and so if I take the derivative of this thing, it's just going to be equal to 0. And we can connect that back to our definition of derivatives by looking at the graph. If I have h of x equals 7, that is the graph of a horizontal line at y equals 7. And so the tangent line, or the slope of the tangent line at any point, would just be a flat line, because the whole thing's a flat line. Or in other words, it would just be a slope of 0. And so we can intuitively check that with our graphical representation and confirm that that's just 0. Okay, the last one, the square root of x can be written as x to the power of 1/2. So j prime would be 1/2 x to the power of 1/2 minus 1. And 1/2 minus 1 is -1/2. So I could write this as, x to the power of -1/2 over 2, or 1 over x, or 2x to the power of positive 1/2, and turn that x to the power of 1/2 back into a square root function. So the square root, the derivative of the square root of x is just going to be 1 over 2 square root of x. And that's actually a really useful one to know for future assignments. Hint, hint, wink, wink. Okay, some more power rule examples. So we have -7 x to the power 4. These examples only look different from the last ones because they're written as an equation instead of as a function. So that's one difference here. So to use the German guy's formula or notation instead of the British guy's, we could say dy dx for the first one is equal to, well, 4 times -7 times x to the power of 4 minus 1, or -28x to the power of 3. If y equals e, remember that e is just a number, 2.718. That's going to be a flat line. So the dy dx is 0. The derivative of any number is just going to be 0, for the record, in case you didn't know that already. All right, so the next one, we can write this as a power function, x to the power of -1. So dy dx is going to be equal to -1 times x to the power of -1 minus 1, which is going to be negative x to the power of -2. And we can make that a positive exponent by writing it as -1 over x squared. So there's dy dx for that one. The fourth example we can write as a power function x to the power of -2. So dy dx is -2 times x to the power of -2 minus 2, which would be -2x to the power of -3. We can make that exponent positive by writing it -2 over x to the power of +3. All right, so applying the power rule works with polynomials as well as monomials. You just do the power rule for each term separately. So the first one, dy dx, would be 5 times 3, 15, x to the power of 5 take away 1, which would be x to the power of 4. If you think x, well, 8x, x has a power of 1. So if we do power rule here, it would be 8 times 1, which is just 8. And then if you take 1 away from the exponent of 1, it'd be x to the power of 0. Well, anything to the power of 0 is just 1, so it'd be 1 times 8 times 1, which is just 8. So really, if you have a derivative of a linear term like 8x, just hack off the x and you're good to go. We get that same example here. The next one, 3x, we're just going to ax the 3, or the x off of the 3. We'll do the power rule in the first two terms. Notice the constant terms, the -3 and the +2 on each of these. Well, the derivative of just a constant term is 0. So technically it's plus or minus 0, which basically is just a wash. So when you derive things, the constants drop off every time. All right, takeaways. We can now distinguish power functions, and when we see those power functions, we can use the power rule to derive them.